So let's see what kind of minimum spanning tree would Kruskal's algorithm build on the graph that we had in the last video. So we're going to pretend that we are looking at the edges in increasing order of weight. So the first edge that Kruskal's algorithm will consider is this edge of weight 1. Obviously it does not create a cycle, and so we are going to add it to our growing spanning tree structure. The next edge that we will consider is this edge of weight 2. Now adding that in still doesn't produce a cycle, and so we're going to add it in, and so our tentative structure looks like this. Our tentative tree structure looks like this. The next edge we will consider is this edge of weight 3, but adding it in is going to make a cycle with the earlier two edges, and so we don't add it in. So we're going to pretend that our growing structure is given exclusively by the red edges. The next edge the algorithm will consider will be an edge of weight 4. Now it so happens there are actually 4 edges of weight 4. So when there are ties like this, we can consider the edges of weight 4 in any order that we like. So let's say we consider this edge first. So adding this edge does not create a cycle, so we'll add it in. Then we'll look at the next edge of weight 4. So suppose the next edge of weight 4 is this one. Now adding that in does not create a cycle, so we'll add it in. Then we'll look at the other two edges of weight 4. So if we add this edge in, it's going to create a cycle with 3 of the red edges. This one, and this one. So by adding this edge of weight 4, we would have completed a square that would have led to a cycle, so we won't add it in. Likewise, if we try to add this edge of weight 4, it's going to create a cycle with the edges of weights 2 and 4, so we don't add it in. Next we consider the edge of weight 5. Adding that is not going to create a cycle, and so Kruskal's algorithm will add that in. And finally we have this edge of weight 6, which if we added would create a cycle, and so we don't add it in. And so at this point our structure is given by the set of red edges, and you can see that they don't have a cycle and they span all the vertices, and so we have a spanning tree here. What is the total cost of the spanning tree? It's 1 plus 2 plus 4 plus 4 plus 5. So 5 plus 4 is 9, 9 plus 4 is 13, the total is 16. So the minimum spanning tree is going to have a total cost of 16. Now how are we going to implement this algorithm? So this time the graph is weighted, so we are going to assume that our input to the problem is going to be a number n, which is basically the number of vertices, and let's assume that their IDs are again in a convenient range from 0 to n minus 1. Moreover, we are going to have an edge list, let's call it a connections list, which is basically going to be a sequence of triplets. So we will have a source, we will have a destination, and it might be better to call them as u and v rather than source and destination, because we are talking about an undirected graph, so the directions go both ways. And in addition to the source and destination for each edge, we will have a weight field as well, or a cost field as well, which is going to be associated with each edge. So given these two inputs, how do we execute Kruskal's algorithm? Now you might have guessed that this repetitive process of taking the next higher weight edge, trying to add it in, see if it creates a cycle. If it doesn't create a cycle, add it in, otherwise we drop that edge and continue on. This sequence, this repetitive sequence, which considers the edges in increasing order of weight, is dynamically constructing the spanning tree by starting out with potentially a collection of disembodied pieces which then successively merge together to form, sorry, not this, which successively merge together to form the minimum spanning tree. So the union find data structure is an ideal structure to implement the execution of Kruskal's algorithm. Because we have these disembodied pieces initially, we can't use BFS or DFS style code. And recall that the union find code does not require us to build the adjacency list. Instead, what we have is basically a couple of arrays, the size array and the parent array. So we will have the same thing here. We'll have a size array of size n, since we assume that all vertices start out in their own connected component. Each of their connected components has a size of 1. We'll also have a parent array, which is going to be basically an array from 0 to n minus 1, indicating the component ID, or the ID of the leader who each vertex is following. And initially each of them is basically following themselves, and so they are in their own separate connected component. Now the number of components that we have at the beginning are always n, so this is our initialization as before. Now we are going to consider the edges in increasing order of weight. The edges might not be given to us in increasing order of weight, so what we need to first do is to sort the connections list, the edge list, according to the cost field, right, which is the third field in the triplet. So you need to know how to basically sort a list of tuples according to an arbitrary field in that tuple, and how you do this would depend on what programming language you're using, but you should be familiar with how to do that. So supposing that we do that by calling some native library sort function with the appropriate specification for which field to treat as the key, we then go through the connections array. Now it's sorted, so let's go through the connections array one edge at a time. So each entry in the connections list is going to be a triplet. So for each edge that we consider, we are going to have the same code as before. We will find the leader, sorry, this should be u. We will find the leader of u, we will find the leader of v, and then only if the two are not the same, if root u is not the same as root v, which means they belong to different connected components, only then will we unify them. And what does it mean to unify them? It means that the edge that we are considering is going to be added to the growing structure by Kruskal's algorithm. If root u and root v had been the same, that means u and v would already have been connected in that growing structure, and which means that edge u comma v would have created a cycle had we added it in. And so Kruskal's algorithm will ignore that edge if the two happen to be the same. So only if they are not the same will we do something, and what we do is going to be essentially the same as what we were doing before. We will compare the sizes of the two component trees that we have. Depending on which of them is bigger, we will accordingly decide who is going to be the child of whom. So if size of the tree rooted at root u is smaller than the size of the tree rooted at root v, then we are going to make the parent of root u to be root v, and so the size of root v is going to increase by the size of the tree that is now coming under it. Otherwise, else, we assume that this tree is the smaller one, and so we're going to make the parent of root v be root u, and the size of root u is going to go up by the size of the tree that is now coming under it. And as before, whenever we are doing a union operation, we will decrement the number of components by 1. But apart from this basic template which we already had before, we have to return the cost of the minimum spanning tree and potentially the edges of the minimum spanning tree. So how do we do that? So if we have a variable that's going to track the total cost, we can go back up and initialize that variable. Let's call it total cost, and this is the cost of the spanning tree that is going to be built up edge by edge. So it's initialized to 0, and whenever we do a union operation, we are effectively adding the edge u comma v to the growing structure that will become the minimum spanning tree. So we can therefore increment at that point the total cost by the cost of that edge between u and v. And what if we wanted to track the edges that are going to make up our minimum spanning tree? So we can initialize our list of edges to be an empty array at the beginning, and whenever we are doing a union operation, we are going to add the edge between u and v to that growing list of edges. And so once we exit the for loop after looking at all the edges in the graph, we would have the total cost of the minimum spanning tree available here, and we would also have the edges of the minimum spanning tree available there. If the graph had not been connected though to begin with, then the number of components is not going to come down to 1. If the graph was not connected initially, that means there cannot be a minimum spanning tree. There cannot be a tree which spans all the vertices because there is no connectivity to start with. So if we had to check for that, we would just add this additional check that as long as the number of components is equal to 1, we have a meaningful MST, and so we can return either the total cost or the list of edges which make up the spanning tree and so on. Otherwise, we know that the number of components is more than 1, so there is no meaningful MST in that case, and so we will then return some default value which should be specified in the problem itself. So you can see that the code for Kruskal's algorithm is almost the same as the code that we had for the union find data structure for the earlier problems. I have not written the code for the find function because it's going to be identical to what we had before. If needed, you could even add path compression to it, as we did in an earlier video. So let's analyze the complexity of this algorithm. The initialization cost is basically the cost required to initialize the parent and the size arrays, which is basically just order n. So I'm not going to take that into account. I'll just write it here. The bulk of the cost is actually going to be in sorting the input list of edges in increasing order of weight. So if we have m edges here, we are going to have a sorting cost of order m log m, which also happens to be m log n, because in the worst case m is order n square and log of n square is basically the same as 2 log n, right? So this can be written as m log n square, which is basically 2m log n, which is also order m log n. Now if the graph is additionally given to be a sparse graph, then this is basically an n log n complexity. So we have that n log n complexity, and then we have this union find process, which is going to have the same complexity as before, because all that we are doing is we are maintaining an extra variable called total cost and maybe an extra list of edges to which we append each edge whenever we do a union operation. So our complexity is going to remain the same as before, so I'm just going to call it as practically linear time, assuming that we are doing path compression as well. This is going to take order n time. And so when we add up this order n log n time for sorting with this order n time to follow this this dynamic process of adding connections using a union find data structure, the total cost of Kruskal's algorithm comes out to be order n log n. And this is for a sparse graph, otherwise it would be m log n. But you can see that if the graph is sparse, then this complexity allows us to run this algorithm on graphs of several million vertices.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your 3 webinar slot today